Can you hear me? Can you say something, please?
Yeah, good morning, Dr. Meyer. I can hear you.
I can hear you too.
Okay. Okay, let's get started. And today, and because of the weather, through closed. So, but I don't want to waste time. So I want to have virtual Zoom meeting for our class. So let's continue. So this one will be recorded and will be posted on the shared folder also. So last time we talked about the mechanical behaviors and we ended up with this is creep. So this creep is very special phenomena. So it was found kind of recently. So people found that under some condition at this is elevated temperature, even though the load does not change. However, as the time goes, this is a strain and keeps increasing. So this is a new phenomena is termed as this creep. So this creep has three. This is this creep and has a three stage. And the first stage that goes relatively slowly, and the second stage is kind of linear, so the time and this is a creep deformation, and third stage and goes very quickly, and so we can usually lead to the fracture for the third stage. So as I told you guys, so this is the diagram is very similar and to the diagram that we use to describe the fatigue phenomena. So the fatigue, we have a Paris law, P-A-R-I-S, and Dr. Paris. Dr. Paul Paris, Paul, first name is P-U-A-L. Dr. Paul Paris invented this, this is the fatigue life. This is a Paris law. So that's the reason, so this law was named after his name. So as I said, so creep and fatigue, their diagrams are very similar. Any questions regarding this slide? No question? No question. Let's continue. And then we talk about the material numbering systems. So material, and we usually when we ask people and we want to buy some material, and people will ask what material you want to buy. So you need to give and the vendors the material information that you want to buy. So there are several commonly used the numbering system. The first one is SAE, is from Society of Automotive these engineers, and they have their own. This is the naming the convention. The second one is American Iron and Steel Institute, which is called AISI. So this is institute has and their own. This is a convention also. And the third one is Unified Numbering System, UNS. The last one is American Society for Testing and Materials and for Cast Iron. So these is our four commonly used numbering systems. So I'm going to talk about this one. So have you guys ever taken the material science, or are you taking material science? Bobby, you are taking?
I took material science last semester.
You took already. Okay, so about other guys, are you taking material science this semester, or you have taken this one before?
I also took it last semester.
Okay, thank you, ready. Okay, so I assume all other students who did not answer, and they are taking this material science this semester. So AISI is usually very often used this material, we usually see AISI 1045. That is a steel. AISI and 1045 is a steel. Is a commonly used steel. So this is our 4 commonly used numbering systems. And then this we talk about UNIS numbering system. And unified numbering system, it is established by SAE, Society of Automotive Engineers, in 1975. There are several letters. I'm give you some. I will describe some conventions for them. Letter prefix followed by 5-digit numbers. And so this here are how this is what this letter stands for. So this G means the carbon and alloy steel. This carbon and alloy steel. The A is aluminum alloy, and C is copper-based alloy, and S is stainless or this corrosion-resistant steel. So usually the people they use this is the very meaningful the prefix letter to designate the different material different materials. So any questions regarding this slide? No question. We'll move on to next slide. So this is UNIS for steel, and steels, they are commonly used material in industry, in our research. So for steel, and the prefix is G. And the first 2 letter numbers indicate the composition excluding the carbon content. So you can see these are 2 letters, these are 2 numbers indicate the composition. And so, for example, G13 is magnesium, and G23 it contains nickel, and G25 contains nickel also. So second pair of numbers indicates carbon content in hundreds of percentage by weight. So this is the second pair of numbers. 94, for example, this is 96. For this 96, this is first, for example, this 52 and 52 here is chromium. 98 means that it is 0.98% of carbon. Second, this is what this statement says. The 5th number is used for special situation. This is 6. Number 6 here is used for special situation. So if you are given a number for this material, and by using on this slide, and you can just approximately know on what kind of material this guy is. Questions regarding this slide? No question? Let's move on next one. So this some casting processes, and when we build something, and we need to have material. So the casting is this is really one of the earliest the processing processing methods and to build a material. And set casting and shell molding, investment casting, and powder metallurgy, this is the process. So by the way, guys, powder metallurgy process is the precursor of this is currently hot this research topic, the additive manufacturing, the powder. The sand casting is means that we use the sand to build this is the mold, and then we just melt this material, and then we pour the molten material inside this is the mold that is constructed using sand. So then after it solidifies, and we just break, and we just remove the sand, and then we will have the product that we just built. And so this is very important. I would suggest for the shell modeling and investment casting. So investment casting is very similar to sand casting, and you can just take a look at the textbook and to get more details about this method. And by the way, why we use sand casting? Because the sand has very high melting temperature. Okay, so this is the reason, and the humans the ancestors and they use the sand to build the mold, and then use this casting in the sand to get the products. So this is why people start using this sand casting and many years ago, maybe thousands of years ago. Questions regarding this slide? No question? Then we talk about next slide. We have talked about the cold working process. Now we talk about hot working process. And I told you guys what's the difference between the cold working and the hot working. The difference is that the operating temperature. For hot working, the operating temperature is above the recrystallization temperature of the material. So cold working means that the operating temperature is below the recrystallization temperature. So this is the difference between this cold working and hot working. So also in the manufacturing processes, and the author differentiated a little bit further. They have hot, warm, and cold working. And we will talk about that one in our manufacturing process class. For here, if I ask you how many the working process you have, you can give me cold working and hot working. That'll be good enough. So what is the purpose for hot working? So we can refine the grain size because of high temperature. And we usually, because the temperature is high, the surface finish is not good. It's not as good as the cold working. It's not as good as the surface finish we got from the cold working. So they have rough surface because of high temperature. So for example, rolling, forging, and extrusion and processing. And why we need why we need to use high temperature? Because at high temperature, so these materials they are becoming more ductile and much easier to be processed. For some cold working, sometimes for some material, you cannot do anything because it is too hard, too stiff. So here are the bar cross sections from the hot rolling. The rolling, if you have internship already, you might see this kind of what kind of products you have. This is round, square, half oval. So this is flat, this is hexagonal. So this is a bar shape. And then you have a structural shape. This is wide flange. This is this I structure. So this is a channel, and we call C structure. And this is angle, we call L structure. So this is a T with T structure, and this is Z, and we call this Z structure. So these are usually the products we have from the hot rolling. So any questions regarding this slide? No question? We talk about next slide. On the cold working process, so forming of metal without elevating temperature. So this is below, that means operating temperature is below the recrystallization temperature. So strain hardens and resulting in the increase in the yield strength. I told you this is a the stress strain curve, and we will have, if we do some work, and we will strain harden the material. So this increases the hardness and ultimate strength. However, so this cold working decreases ductility. So produce bright, smooth, reasonable, accurate finish. Why? Because this is the operating temperature. So cold rolling used to produce wide flats and sheets. So in the ME, mechanical engineering lab, we will have previously, we have a lab session to let the students get this hands-on experience of cold working. The cold drawing draws a lot of a hot rolled bar and through a smaller die. So cold drawing draws a hot rolled, and this hot rolled means that this bar is built by hot rolled. Okay, so this is already done. This is already done. Its temperature is still go to the room temperature. So don't get confused. Hot rolled here means that this bar is manufactured by the hot rolled, and now I want you to do the cold draw of this bar. So you can see these diagrams. So this is yield strength, yield point, and this is cold draw. So this is hot rolled, this is yield press, this is cold draw, hot rolled. So this is stress elongation. The yield for this cold draw, the yield point is high, and also ultimate strength is much higher than this hot rolled. Any questions regarding this slide? No question? Next one. And heat treatment of steel. And for some purposes, we need to heat treat the steel and for to satisfy our needs. So when we do the heat treatment, it means that you have a workpiece, the stock or stocks, and before you use it, you need to put this guy in the furnace, or you can use other means, for example, the cold water or the cool oil to do something. So time and temperature. So this is two important the variables for the heat treatment. Time, how long you do it. Temperature, at what temperature you want to process this material. So this is time and the temperature and modify the material parameters. So I want you guys to know for heat treatment, the two most important factors are time, the length of time, and temperature, the operating temperature. Okay, so usually we have two commonly used this is heat treatment, the means. One is annealing, one is quenching. Annealing, okay, annealing, you heated the material, the workpiece is heated above critical temperature, and then this temperature is held constant, and then after some time, and it is cooled slowly. Right, the cooling rate also plays a very, very important role. It depends on your needs. So this annealing, because of high temperature, so it refines the grain structure and makes the structure softer, and also it increases ductility. So why? Because the high operating temperature. It erases memory of prior operations. Erases memory of prior operations. Why? Because the grain size refined, it softens. So normalizing provides partial annealing by adjusting time and the temperature. So underneath the umbrella of annealing, and there is a subdivision, sub-branch, which is called normalizing. So normalizing provides partial annealing by adjusting time and temperature. So this is annealing. Annealing, the characteristic of annealing is that you use high temperature. So second one is quenching. The quenching means that, as the name suggests, quenching means that you put some hot items just in the cold medium. For example, water, or this cold oil. So controlled cooling rate prevents full annealing. So you want to cool it. So less perlite, more martensite, and or bainite. So if you are taking this is the material science class, and because now it is just the beginning of the semester, I don't think you know this perlite, martensite, or bainite. So however, if you have already taken this material science course already in the previous semester, and you already know what is a perlite, martensite, and this bainite. So these are three microstructures for this is a steel, right? So they have different hardness, and they have different the grain size. And the martensite, usually the quenching is corresponding to the martensite. When we quench something, and our resultant material microstructure will be martensite. Martensite is very, very hard, and also it is very, very brittle. So this is increase the strength, hardness, and brittleness, because this is martensite. Okay, and I want you guys to write down for the quenching, and the resultant microstructure is martensite, and which is hard, which is much harder and also much brittle, much more brittle than perlite and than bainite. Questions regarding this slide? No question. Let's move on to the next one. And another this heat treatment is a tempering. For tempering, reheat after quenching to a temperature below the critical temperature. So you should know that the tempering is the sequential heat process after this is a quenching. After finish quenching, as I said, the martensite is very, very brittle and very, very hard, and usually you cannot use it for your industrial needs. And then this is the reason that you need to temper this martensitic material. So tempering, after the quenching, you reheat. This is a quenched material to a higher temperature. And then why? What is the purpose? You want to relieve some internal stresses. And this will increase the ductility and slightly reduction in the strength and hardness. But it's still very, very good in terms of strength, in terms of hardness, and in the brittleness is decreased. Any question regarding this one? So annealing, quenching, and tempering is the three most important these heat treatment methods. Questions? No question. Let's move on to next slide. Next slide is the effects of this heat treatment. So here is a tempering. So they talk about tempering. Tempering conditions. So here is we have tensile and yield strength. Here, this is ordinate. So this ordinate is Brinell hardness. Here we use the Brinell hardness. So you can see as the temperature goes, as temperature increases, tensile strength, yield strength, and Brinell hardness, and they drop very, very quickly. And however, because the high temperature, so the elongation, reduction area, and both of them, and they are indicators of the ductility. And both of them, they are increasing decently. Right, so here are the conditions: normalized, azoted, and annealed, and you can see on how the tensile stress, yield strength reduction, elongation, Brinell stress, and they are increasing. Questions regarding this slide? No question. And then we talk about next one. It's called this is the case hardening. So case hardening, what is a case hardening? Can somebody tell me what is a case hardening? Hey guys, can you show me your faces? Do you mind? If you mind, I'm okay. Can somebody tell me?
Isn't case hardening when you essentially heat the outside of the piece of material and then quench it to alter the molecular structure so that the outside is hard, but the inside is still ductile?
Yeah. Good. It's very close, but not exactly correct. Okay, it's a case hardening means you get a case, and usually the case hardening we have a chamber. I want to tell you guys this. So this is important. I want you to know this. This is how it is conducted. So the case hardening means that we have a chamber. We have a chamber. Within this chamber, we can add some material, some gas. So this can be solid, liquid, or gas that has high carbon. So this, and then we put our material inside this. This is the chamber, and then we close it, and then we leave. We elevate the temperature, and then we hold this temperature for a certain period of time. And during this time, so these are high carbon. This is items, the carbon items in the solid or in liquid or in the gas, and they will diffuse on the surface of the workpiece and you are interested in. So as a result, right? As a result, after you have finished this case hardening, so after you take out your material, and you can see on your material the surface will be much harder. However, the internal part is still decently soft. So this is called case hardening. Case, you must have a chamber. Hardening means that inside this chamber, and you have some high carbon materials, either solid, liquid, or gas, and then you put your material, put your workpiece inside this chamber. Then you elevate temperature. After some time, so this case hardening is finished. So I want you guys to use your own language to describe the case hardening. You have sense? The key word is you must have a case chamber, the chamber, the sealed chamber. And this chamber contains solid material or liquid material or gas, and then which has high carbon, and then you put your workpiece inside it at elevated temperature. So heat treatment, only the outer surface. Okay, this is one kind of heat treatment. So you will have outer surface. The outer surface is very hardening is very high. So you can also do the induction hardening or flame the hardening. Questions so far? No question? No question. Let's move on to the next one. Next one, we talk about alloy these steels. Steel means that it has iron. Alloy steel means that we add some other alloying elements. And for example, we add, this is a chromium, nickel, magnesium, silicon, molybdenum, neridium, and tungsten. So this is, we put different elements together, and we call this is alloy. Alloy means that we have multiple elements together. So this is a corrosion resistant steels. So these corrosion resistant steels, and we the stainless steel. Let's see the stainless steel. Stainless steel, they are commonly used in our daily utensils, right? Daily utensils, and we use stainless steel. This iron-based steel with at least 12% chromium, and resist many corrosive conditions. So this is one thing I want to mention. Okay. So this author and use this number 12% chromium, but some authors they use 9%. Either way will be okay. Okay, guys. So because I have not done the experiments by myself, I just believe what the authors say. So there are several types of stainless steel. And first one is ferritic. It's chromium. Ferrite is another the microstructure of the steel. Ferritic, chromium, austenitic, chromium, nickel, martensitic, precision hardenable is a stainless steel. Martensite, austenite, and ferrite, there are also three different microstructures of steel. So after you finish your material science class, and you will have better understanding of these three concepts. Any questions regarding this one? Based on this slide, I might ask you, and in order to achieve the stainless, this purpose for steel, and what is the percentage of chromium you need? And you should use 12%. Okay. If you say 9%, you tell me, say, so based on another textbook, and the author says 9%, I'm also okay. You have sense? Okay. Let's move on to the next one. Next one, a casting material. The casting, as I said, casting, and we use the commonly used casting method is the sand casting. So we have green cast iron. We usually the iron we cast iron. the ductile and nodular the cast iron, wet cast iron, malleable cast iron, alloy cast iron, and cast steel. So the details, I want you guys to look at these details in the textbook, or you just carry all these questions, all these concepts in your material science class, and to get a better understanding of these concepts. This is iron, different conditions. Next one, non-ferrous metal. We talk about the steels, and steels because all of them they contain the iron. They are called ferrous steel. So non-ferrous steel means that non-ferrous metals that means that these metals do not have iron. For example, aluminum is commonly used because of the lightweight. Magnesium, titanium is commonly used because of this is the service life. And also copper-based alloys, and the copper-based alloys, for example, brass with 5 to 10% of zinc, to the brass with 20 to 36% of zinc, and with 36 to 40% zinc, and bronze. So we have the humankind, the humans, and we have the age called the brass age, right? Brass age. I forgot the exact the time range for the brass age. After brass age, it is the iron age. And before the brass age is the stone age, new stone age. And stone age we have two, old stone age and new stone age, and then brass age, and then iron age, and then we have this silicon age now, and we are in the polymer age. There are now currently a lot of, let's say, versions. Questions? You can see the human history can be characterized using the materials and the people are using. No question? Move on. Next one, plastics. So this kind of, we can say this kindly recent, and we have two different kinds: thermoplastic and thermoset. And thermoplastic, any plastic that flows or is moldable when heat is applied. So it change. Okay, so it's very easy to flow. That means it is softened. So thermoset, a plastic for which the polymerization process is finished in a hot molding press, where the plastic is liquefied under pressure. So these are two different the plastics, and we have in our daily life. So here's the thermoplastic properties. So different, these commonly used the thermoplastic materials. And so this ICU is ultimate strength, Young's modulus, the hardness we use Rockwell, and we have this elongation percent, and the dimensional stability, heat resistance, and chemical resistance, and processing methods, processing means. All of these materials are given here, and for the commonly used thermoplastic, this is groups. I will not go into the details, and you can just take a look if you are interested. My purpose is that I just show you. So this is the sketch idea of these commonly used thermoplastic properties. Questions? No questions, and move on to the next one. Thermoset is in the second this category of the plastic material. A thermoset, and we have the commonly used one, and we have ICU, this ICU hardness on those processing methods. They are given here. You can see heat resistance for this thermoset are much better. Almost all of them, they are excellent. This one is good. Chemical resistance, so this is fair. So this is good. This is excellent. This one is good. Questions? No question. And then we talk about composites. So we have several the basic materials. They are metals. The first category is metals. Second category is ceramic, and third category is the polymer, and the fourth category is composites. And for composites means that we have two or more the basic materials, and that's called composite. So formed from two or more dissimilar materials, each of which contributes to the final properties. Materials remain distinct from each other at the macroscopic level, and usually amorphous and non-isotropic. Often consists of laminates or of filler to provide stiffness and strength, and the matrix to hold the material together. The common filler types. They are common filler types. Particularly the composites, you can see. So I have a matrix. Matrix is a body, the major body of this material. And within this material, I have some particulates, other material. So this one, finally, so this whole material is called composite. So second one is steel. We have a matrix, which is a major the body of the material. And then we put this is the randomly oriented short fiber, can be glass fiber, or can be this is the and other fibers, the carbon fiber. I'm working on the carbon fiber material now, the milling of carbon fiber, manufacturing of carbon fiber, reinforce the polymers now. So this is the carbon fiber. And then for this one, we have unidirectional continuous fiber composites. So this white, the area stands for the matrix material, the major material. And then we put the fibers inside. So this whole material will be called unidirectional continuous the fiber material. So this woven fabric. So we not just have this directional fiber, we might have this horizontal these fibers. So this is called woven fabric composites. In our daily life, we see a lot of composites material. For example, the sweater I'm wearing now. Okay, this is the fiber. Questions regarding this one? Okay, so material families and the class. So the metals, so the major metals classes, we have different classes. On the shorter name, we have this one metals. This is a basic, the first basic the material we are using and commonly used in our daily life and in industry. And second one is ceramic. And this is a ceramic. This glass is, we can call the glass is a ceramic also, but because the glass, they are special, we just put it here also. The ceramic, technically ceramic, the fine ceramics capable of load bearing application. Non-technical ceramic, the porous ceramics of instruction. So we have different classes: aluminum, nitride, boron carbide, so on and so forth. So here is, so tungsten carbide is used for the manufacturing tool, the tool insert. Okay, so tungsten is very, very hard. And silicon carbide is also boron carbide. Let me see all of these materials, and they can be used as the cutting tool. Why? Because they are very, very hard, and they does not change too much. The shape and size does not change too much, and at the elevated temperature, very hard, and this is the stable the property. So this is for non-technical the ceramics you can break for our this is construction in our buildings, our home, brick, concrete, stone. And for glasses, we have different glasses. We have soda lime glass, borosilicate glass, silica glass, and glass ceramic. So this, as I said, glass, because we use glass very, very often, this is very close to us. We just, the author just categorized it separately. Any question regarding this one? So by the way, all these materials on these slides, they have very, very high melting temperature, and they are chemically stable, and also they are very stable at high higher temperature, even before the melting. Questions? No question? Move on to next one. This is the third, the basic material, the polymer. Polymer and the different things, they have thermoplastic and thermosets of engineers. They have different classes, and the short names are given here also. And so if you are interested, and you can just take a look. And by the way, so this is a polymers, and they have a polar. Polar means multiple, right? Mer is the single unit, and polymer is multiple single units. They put things together. So this is polymer. This is research is huge, and so it is very, very hot because it is closely related to the chemistry. Questions regarding this slide? No question? And then this is elastomer, and it's a hybrid. Hybrid, we have composites, foams, and natural materials. For this elastomer, for example, engineering rubber, natural and synthetic, either natural or synthetic. And we have elastomer here, so commonly elastomer. And so here is a shorter names for them. So hybrid, the composite is a hybrid. So usually this one is referring to the artificially composite material. The foams, foams, you know foams, right? So, and also natural bricks, for example, cork, bamboo, wood, and they are hybrid. So they are hybrid, and they are natural materials that we can use for our daily life and for industry needs. Questions regarding this slide? Okay. So this is Young's modulus for various material, and so let me move this bar. So here is the Young's modulus, and so here is, you can see that different material. Tungsten carbide is very, very high. Young's modulus is very, very high, and low alloy steel, nickel alloy, copper alloys, and so on and so forth. You can go here. So here is the Young's modulus is relatively low. Okay, so this is relatively low. So this we know that, right? So we in our daily life we have done something by ourselves, and so tungsten carbide is very, very high Young's modulus and also high hardness and high melting temperature. That's the reason. And tungsten carbide is commonly used as the material for the tool inserts, for the manufacturing tool. I want you guys to write down, okay? Tungsten carbide. Write down, guys. Tungsten carbide is a commonly used material for the cutting tools. So I still want you guys to remember to memorize some facts. The tungsten carbide, you know tungsten carbide. Questions regarding this one? No question. We'll move on to the next one. Sorry. So this Young's modulus versus density. So this is density. So here is the Young's modulus. This is Young's modulus. Young's modulus versus density. Okay, so here, so this area, and they have low density, but low Young's modulus. And here, and they have high density, but they have high Young's modulus. You can see these materials. So aluminum oxides, and these silicon nitrides. So these materials, and they have the high density and the high Young's modulus. So here is the decent density but the low Young's modulus, and so here this area is also decent density but the decent. This is Young's modulus. So this figure, I'm just to show you whenever you think you are considering the density and the Young's modulus and which material, and you need to find which area, which material group, and you need to focus on. Questions regarding this one? Okay, so the species volumes, so species volumes, it is the ratio of Young's modulus to the density. So also it's called the specific stiffness because the Young's modulus is the indicator of stiffness, and it is useful to minimize weight with primary design limitation of deflection, stiffness, or natural frequency. And parallel lines, you see these are parallel lines here, the dotted parallel lines, and they are representing different values of E/P. This allows comparison of specific modulus between materials. Questions regarding this slide? No question? Then this is the minimum mass guideline for Young's modulus density plot. So the guideline plot constant value of this E beta B rho. Okay, rho is a density, and beta depends on the type of loading. So axial loading and so bending loading. So this one is also based on the empirical equation. So this is empirical equation. For example, for axial loading, we have K here. So we have this is A equals KL divided by E, M equals this one. So to minimize the mass, maximize E over P. So when beta equals 0. So you can see this area, and so this area. So this one, so this line, you can see this line is E divided by rho, E divided by rho. So this is a very, very nice figure diagram. Any questions regarding this one? No question? The performance metric depends on several things. First one is functional requirements. Second one is geometry, and third one is material parameter. So this P is a performance metric, is a function of these three guys. The functions is often separate, right? So these are three different functions. So F3 is called material efficiency coefficient. So maximizing or minimize this one allows the material choice to be used to optimize the P. So this is from the perspective of optimization and of optimization engineer. The performance metric example requirements light, stiff, and loaded a cantilever beam with circular cross-section area. Mass, stiffness is functional requirement. Stiffness related to the material and geometry. You can see. So based on these equations, and we want to get this performance metric example. So this is a deflection. How to calculate this deflection? This is I is area moment of inertia. So this A is area, right? So this M, this is related to the rho, and then we calculate this M here. So M, and then we have this P here, okay? The P, we want to calculate the P here. And so this F3, F1, F2, F3, to minimize M, we need to minimize F3. So to maximize this one. So then you go back to the slides and to get on which material and we can get this, satisfy these needs. So this example, M is called material index. For example, for this one, beta equals 1/2. Axial, this is depends on the loading conditions, and you use this guideline, increase M. Good candidates for this example are certain wood composites and ceramics. So you can do additional constraints can be added as needed. So for example, here Young's modulus, and you can just, if Young's modulus, it must be greater than 50 GPa, and you need to draw a horizontal line to limit the solution space base. Wood is eliminated as a viable option. Okay, the strength and